All right, I just wanted to add a little bit more to the discussion of like quality energy and kind of rush there at the end. So, with this graphic that's found in your book, um, you have just the idea of when we come to high energy, whether it's high temp, so the on the right talking about like different temperature heat and how it might be used. So the higher the quality of energy, the more work that can be done from it. So when we talk about high temperatures, you've got this list of what are some things that can be done with high temperature heat, from the production of electricity and different industrial processes that require high energy. And then your left side being fission, fusion, um, and all of the energy associated with it. And then you've got kind of your in-betweens that you can kind of look at. And then when you look all the way down on the bottom, you've got dispersed geothermal energy, so low temperature heat. So if you might have a house that has a heat sink where you draw heat from the soil outside your house, so very dispersed geothermal energy, and then you use that to kind of regulate temperature in your house. That might be a way of using low energy or low quality energy to do something. All right, so now let's talk just a little bit about changes in matter. So you can have physical changes in matter and chemical changes in matter. Physical changes in matter is going from a solid to a liquid, or from a liquid to a gas, or even from a gas to plasma, I would imagine. And then chemical changes in matter, that's when you have a change in what the substance is. So rearrangement of atoms to form new compounds from old compounds. So an example of a chemical change or a chemical reaction here. So here we have solid carbon combining with oxygen produce carbon dioxide, and in that process you would give off energy, because this would basically be combustion. Or an example of carbon combining with oxygen would be like the burning of coal, is an example of this, where carbon dioxide is one of the products, and then heat given off, or energy, is the other, and then harnessing that energy is usually how we utilize coal. Actually, but I'll go back. So with here you have carbon, you have oxygen. They're two different compounds, and they come together to form carbon dioxide. And in the process, you break the double bond of the oxygen gas and produce two double bonds between the oxygen and the carbon on both sides. But in that process, you actually give off more energy than you consume, and so therefore one of the products is energy. All right, within this discussion of matter and elements, the law of conservation of matter is an important component of that. I'll go back, sorry. And the law of conservation of matter states that no matter what you start with is what you end with. That's important. So matter is not destroyed, it's simply kind of rearranged. It only changes form. So maybe it goes from a gas to a liquid, or maybe it was a solid and then it combined with something to become a gas. So there is no throwaway, and that's the important piece, at least the connection to environmental science, is that no matter what you produce, whether we produce, plastic packaging, or you have a large, you know, building or a dam, you can't throw it away. There's nowhere to put it. Yes, you can go put it in a landfill, but it's not going away. The matter isn't going away, and we're kind of stuck with it. Okay, so making that connection between matter and pollution. So some pollutants, pollutants have a chemical structure, right? So if we talk about DDT, which was used as a pesticide in in the 50s and 60s, um, you know, when we think about a pollutant, one of the components of it is how concentrated is that pollutant in the environment. Is it really minute? Is it very, very, not, very, very low concentration, or is it a high concentration? Another piece of that, how persistent is it? How long does it last in the environment? Will it break down quickly, or does it last for years and years and years? One of the issues with DDT is it lasts for a long time. It's still affecting the ability of like bald eagles to produce eggshells because it's still in the environment. It gets into into food webs and is impacting organisms. So this same idea of degradable, um, de the production of degradable pollutants, although they are pollutants over time, they don't have a long-term lasting kind of presence. And then you can produce biodegradable pollutants, or or just the idea of a pollutant that is biodegradable. So if you think of like human waste, like you know fecal waste or all of our sewer kind of products, that stuff is biodegradable. So it can be broken down and then eventually it's reused or reused. But it is still a pollutant. If we just dumped our sewage directly into the ocean, that would have some long term or some at least some short term pollutant issues as far as water quality, bringing in disease. So although they are biodegradable and that's a good thing, they are still pollutant. You wouldn't want you wouldn't want Blaine's waste pipe just pumping right into Drayton Harbor, for instance. And then there's also slowly degradable pollutants, things that take a long time to degrade, but they will eventually. Some plastics, things like that. And then there's, of course, non-degradable pollutants, things that, for all intents and purposes, are not going away. They're going to be here for a long time. So how can we reduce even the production of non-degradable pollutants? Okay, now we're going to talk real briefly about nuclear changes and nuclear chemistry. So, like I said in class when I was talking about carbon-14, there are things that undergo natural radioactive decay where they're slowly, so this is related to what are radioactive isotopes, things that because the nucleus for one reason or another doesn't have the right ratio of neutrons to protons, it's going to decay. It's going to either shoot off some type of radiation in the form of an alpha particle or a beta particle or even a gamma particle or a gamma ray to modify that nucleus so that it changes in such a way to become more stable. So gamma rays are one of the types of radiation that come off in a radioactive decay. Another type of particle that's detectable is an alpha particle. Now, gamma ray is just high energy electromagnetic radiation, so like visible light, but much higher on the energy scale. Alpha particles, on the other hand, are two protons and two neutrons being shot off, and so very large in the sense of mass. So lots of mass. It's the equivalent of a helium nucleus. So has a mass of about 4 AMUs, which is pretty big. Um, and that also makes it that alpha particles, although are radiation, are since they're so large, they can actually be shielded pretty easily by um, paper towel. A cardboard box would block alpha particles from like penetrating something. So like your skin is a good barrier from alpha particles. You wouldn't suffer excess radiation exposure if you were exposed to alpha particles. And uranium, so if you think of uranium ore, which is used in nuclear reactors and things like that, uranium is an alpha particle emitter. So when it decays, it gives off alpha particles. So when people manage or work with uranium, you actually don't need, like, you have to wear appropriate protection and you'd wear like a respirator, but you don't necessarily need to be covered in like 4 inches thick of lead or something to kind of block it off. You just need appropriate gear that can shield you from it, but nothing overly excessive is necessary. And then beta particles are another type of radiation that would come off, and they are consider them as being like an electron. They're the size of an electron. They're charged like an electron. They get shot off from a nucleus to try to make that stable. And a beta particle is shot off when a neutron turns into a proton. So a neutron is neutral, and for a neutron to become a proton, it needs to become positive. So it shoots off a beta particle, which is a negative charged particle, to leave behind this positive charge. And one thing, and I would ask that you would reference or look at the table on page 49 regarding half-life. And half-life is, so let's say you have some sample of radioactive material. The half-life of that radioactive material, so let's say it's 67 years for this substance. So it's whatever it is. Then that means the half-life of that substance is how long it takes half of that source to decay into something new. And so that's the half-life. And it keeps getting cut in half. So if it takes 50 years, the half-life of, let's say it's called, I don't know, Cutonium. So Cutonium has a half-life of 50 years, and I have 5 grams of it. Well, after 50 years, 2.5 grams of it is still radioactive. And then after another 50 years, 1.25 grams of it is still radioactive. So over time, it halves. Half of the material becomes something else. And so after about 10 half-lives, we typically say after 10 half-lives of some radioactive material has passed, then it's safe to be near. Now, the unfortunate thing is, especially with our nuclear waste and nuclear power plants, the half-life of that stuff is hundreds and thousands of years. And so for 10 half-lives to occur, it's beyond basically human civilization. And so finding places to bury it is really the only viable option, because we're not going to be able to wait it out until we can kind of go near it again. And I kind of already discussed ionizing radiation. So having enough energy to be able to damage or ionize atoms within our tissue, which causes mutation and potentially cancer. All right, so here's that figure that I was discussing, but the idea of, so here we have plutonium-239. It has a half-life of 24,000 years. So after 24,000 years have passed, half of the material will have been turned into something else. And then another half-life passes, another. And as you can see, like, you quickly lose a large majority of the material once you go through 3 half-lives. But keep in mind, that's a significant amount of years. What is it? Oops, sorry. I'm going to go move this over here. That's what, 72,000 years? You're not going to stick around waiting for that to dissipate, so you're going to find some place to bury it. So, all right, 2 types of nuclear reactions that occur, one being fission, one being fusion. Fission reactions are when you have big, heavy atoms that break apart into smaller atoms, and in that breaking apart, and what's breaking apart is the nucleus, so the nucleus, the core of the atom, gets broken apart into 2 smaller atoms. So in case, the example here of fission of uranium-235. So a little neutron gets shot at the nucleus of uranium-235. That makes the nucleus of uranium even less stable. It breaks apart and you get krypton-94, 92, and barium-141. And then 3 neutrons get shot off. 3, and then they go collide with 3 other uranium nuclei. Those split off, and then it just keeps repeating. And so you get, if you don't control it, you would get a uncontrolled fission reaction, which is what a fission bomb does. But with like fission reactors, you actually kind of control the reaction, so you limit how many neutrons are able to find more nuclei to break apart. Fusion, on the other hand, and one of the drawbacks of fission is that Krypton 92 and barium 141 are radioactive, they're unstable. And so you have waste material after you've done the reaction that has to be stored somewhere and is unsafe. Fusion, on the other hand, is when you, at very, very high temperatures, fuse together hydrogen atoms. And you fuse them together in such a way that you produce helium nuclei. And there's lots of energy that's given off when you fuse atoms together. I mean, the sun is where fusion is occurring all the time. And so, with that, you have lots of energy associated. The challenge that is occurring right now on Earth to develop fusion reactors is to create a vessel that can maintain 100 million degrees Celsius at any given for an extended period of time. Okay, so we have some laws that kind of govern how energy works. So the first law of thermodynamics states that energy is neither created nor destroyed. It is simply transferred. It moves from one form to another. And you can't get something for nothing. So energy goes in, energy comes out. But it's often, think of it, what we were talking about a little bit earlier, that it's the quality of energy that you have. So let's say you have really high quality energy to start with. Over time, it kind of dissipates. And that kind of leads us into the second law of thermodynamics, which is in every transformation, some energy is converted into heat, and that heat is lost to the surroundings. So we were talking about systems, so that's kind of thing we look at, and then the surroundings is everything else, and that heat goes into the surroundings, and it's just kind of lost. It's out there, but it's so minute, it's so there's no function for it that over time things are tending towards to lower quality energy. Sorry. Boop. All right. All right, so how do we connect these? So high throughput, so a high throughput or waste economy is one that where they use lots of matter and it just lots of waste is produced in that sense. And then a different type of economy or a different approach would be you consume a lot of matter, but you recycle it. So you're constantly reusing that matter over time. And then a low throughput economy is one where the focus is rather than recycling is on reducing. Let's not consume as much material, as much matter to sustain the life or the lifestyle that we have. Okay, and this graphic kind of talks through, you know, or walks through kind of the idea of how the environment utilizes matter and whether or not we can utilize some of or model the way that we consume after how the environment utilizes resources. So the idea of energy conservation, waste and pollution prevention kind of uh, allows for a sustainable low waste economy, and an output of that is you're always going to have low quality energy coming out of it. Heat is going to be consumed and lost. But with that, you also have pollution control and you've got some waste and pollution. But can you recycle and reuse that material over time? I think that is it. So we will see you. Well, I won't see you on Monday, but I'll see you on Tuesday for the test.